member will be regarded as a tension member. So the member to axial tensile forces are called tension members. So actually, this is a line element where the forces are tensile. So what are tensile forces? These are the forces which elongates or tend to or try to elongate the member. So bending due to simultaneous transverse loading and buckling are significantly reduced, and initially non-straight member tends to straighten up. So actually, if we are having two steel bars uh, which are subjected to tensile forces, one steel bar is perfectly straight and other steel is initially crooked. Maybe it is bent in out of plane direction, mean that it is not perfectly straight. So both steel bars, when they will be subjected to tensile force, if their diameter, length, and material is same, then the both will break at a same load. This means that if there is any initial geometric imperfection, if initially the bar is not straight, it is initially crooked or bent. So this initial imperfection, they will not affect tensile capacity, because even though the bar is bent, first when we will apply the load, so it becomes straightened, and after that it will start taking the load, and it will only break or fail when applied stress will be more than material strength. So what are the typical example of tension member? So typical example are main member of trusses. So in trusses, you know that trusses is comprised of line elements which are concurrently joined in triangular pattern. So the trusses members are subjected to axial tensile force or axial compressive force, because the load is only acting at panel point or at a joint. So a typical example will be the tension member in trusses. Some other example I will show you in the next slides. However, some secondary member like tie rods, certain braces may also be subjected to tensile load. So what is a tie rod and other bracing member? You will see in the next slide. I have some pictures. So in general, the use of single structural shape is more economical than built-up section in case of a tension member. However, however, built-up member may be required in following section. So first of all, let me show you the some tension member. I will come back to built up section and I will explain you. So for example, here, uh, this is a truss. So in this truss, if the load is acting at this top joint or this panel point, so this due to this applied force, all vertical member, this vertical member will be in compression, this diagonal member will be in tension, and all the bottom chord member, they will also be in tension. So in this truss, what is given? Actually, we know the length of this member. The length of this tension member is the panel length, and we know the load from the applied load. We know the internal load effect. This means that we know the tensile force which is acting in this member from our knowledge of structural analysis. So it means that we know the applied load effect, and only unknown is the cross section area. So just like in this truss that you can see, so you can see that all these members, they are comprised of certain steel structural shape, and this shape may either be angle section, this may be channel section, and this may be you can say that W wide plane section. Okay, here you will see that all the truss members, they are not directly connected with each other. So there is a one plate, it is used, which is used at each panel point or joint. So each member is connected with a plate, and that plate is also connected with other members. So all members, they are not directly connected with each other. So this plate is referred as gusset plate. So we will learn about the gusset plate in detail in our subsequent lectures. So other example of tension member will be, this is a cable stayed bridge. So in this cable stayed bridge, the bridge deck is supported by a cables. So in this cable, due to the gravity load in the bridge deck, a tensile load is acting. So it means that if we need to design this cable, design means that we know the length of the cable, we can compute maximum force, tensile force acting in this cable due to the applied load. And what is unknown only the cross section of this cable. This is another example of cable straight bridge. And for example, in some cases in trusses, we are using rod which are called tie rod. And this tie rod which are used in the bottom as a bottom cord, instead of steel structural shape, we are just using a rod. So this rod is subjected to tensile forces. Unknown will be diameter. Okay, here there is another example of tie rod. Uh, Here you can see that we are having maybe a shade on entrance of maybe any building. So this shade, one end is fixed maybe here, and the cantilever portion is maybe connected on the one side with a rod and other side is fixed with wall. So this overhanging portion is supported with a rod. So this is may also be called tie rod or simple rod. So due to the gravity load in this particular rod, a tensile force will be acting. So we know the length of this rod, we know the total load acting, we can compute the total force in this rod from our structure analysis. So if we know the material strength, we can compute what is the minimum diameter required to resist the dead load of this shade safely. So if the diameter required is 12, we may provide 13 or 14, but we may not provide any larger diameter due to the economic reason. So here, I told you that in most of the cases, in tension member design, design mean that we want to select a cross section. We usually select a single section, single member, which is only a sole member, and that shape may be maybe I shape, maybe channel or angle. But sometimes we may select a built-up section. Built-up section, what is a built-up section? First, I will show you, then I will come back. Built-up section is a section which we make by combining two single sections. Here, there are two single sections, angle section, they are placed very close to make a one member. How this arrangement is made, I will explain you. We can also place this single angle in this position. Their corners are facing. And here we are having two channels and their flanges are facing each other, and they are might be connected on the upper side and bottom side by a thin steel member, which are called lacing. So I have shown this lacing member with dash line, dot line. Dot line mean that their area will not be computed, will not be considered in order to compute the stresses. It means that we ignore the area of lacing because this lacing area is not available throughout the land. I will show you some picture that what are these dash line and what are these lacing members. These are small members which are used to connect two single section to make a built-up section or make a one unit, and they are intermittently connected. So similarly, we can place two channel sections. Their web may facing each other and flanges inverted on the outward side, and on the top and bottom we can connect with lacing member. Similarly, we can have the arrangement of four angles and one single steel plate to make I section. And in this case, we are having four angle sections which are placed at a larger distance, and what we are connecting from the outer side intermittently with a small or thin steel member which are called lacing. So this is the lacing. Okay, here you will see that we are having two angle section, two channels, and they are connected on the with flange with some member. So on the edges they are connected with a plate which is called end tie plate, and further the all channels, both channel section, they are connected with a very thin steel bar or flat steel plate, so which are connecting the two channel section in triangular pattern. So this dash line, if I'm cutting the cross section area, it represents this flat or flat thin steel bar. So actually, the area of this steel bar is very less. So we are just representing as a dash line, and we ignore in order to compute the gross area. So what the gross area we will see also today. So here we can also connect two channel sections in this with steel plate which are connecting the both channels in transversal direction. So this is called batten, and this member which are provided in angular pattern are called lacing. We will study this design of built-up section and lacing design in detail in compression member. Here, I just want to explain that how we are making a built-up section. Built-up section or a tailor-made, this is a section that we are making by joining two members so that they will behave as a single unit. Okay, now the question arises that why we want to make a built-up section. So the reason, number one reason may be that tensile capacity of a single rolled section is not sufficient. So what example I want to give you, I need maybe a channel section whose area should be equal to 200 millimeters square. But in market, no section is available whose area is 200. Rather, a heavy section is available whose area is 300 millimeters square. So I will not select 300 millimeters square because that is more than my requirement. Although it will be safe, but it will be uneconomical. Its weight will be more. So what I can do, but in the same market, I am available with two lighter angle section. Each angle section or channel section is having area of 100 millimeters square. It means that if I will join two channel section, then the combined area of two channel section will be 200. So in that case, instead of selecting a very heavy section, I am having an option. I can join two lighter section to meet my requirement. Or number two is to increase the slenderness ratio. Maybe in your mechanics of material, you might know that in the compression member design, the capacity is the function of geometric parameter, which is referred as slenderness ratio. So sometimes what happens, as I told you that we need to design a structural member for two reasons. For applied load or the strength criteria, and number two, stability criteria. Stability criteria mean that there should not be any buckling or deflection. So deflection is the function of moment of inertia or slenderness ratio. Sometimes applied load are very less. So just to resist the applied load, we need very small area. But to satisfy deflection criteria, we need larger moment of inertia. So larger moment of inertia is the function of the larger depth. So it means that if I'm selecting a section whose depth is larger, so it will be uneconomical. So in that case, what we can do, we can place the sections sparsely so that we can achieve the larger moment of inertia. So a simple example I will give you from this section. For example, here you know that I am having four angle section and they are placed sparsely. Okay, now what I will do, if the same section, if I will place very close to each other. Okay, just in this example, you will see that this four angle section which are placed very close to each other, and these four angle section which are placed at a larger distance, they have same area. It means that a larger box section and this section are having same cross section area. We are ignoring obviously this lacing area, but area is almost same. But this the four angle section which are placed very close, they will have moment of inertia very less as compared to the moment of inertia of this four angle section which are placed at a larger distance. Because you know that moment of inertia is the function of depth of the section or height, dh cube by 12. So here effective depth is less, but our in this other case effective depth is more. So we want to, if we want to achieve the larger moment of inertia, so we place the some lighter section at a larger distance, and we can achieve. So it means that instead of selecting the four angle, if I could have selected a rectangular hollow section, so in this way I have reduced this area, I have avoided this area, distance between the angle section throughout the length. So it means that I have made my section economical. So sometimes if a lighter section is not available, or sometimes I need a lighter section with larger moment of inertia so that I can reduce the slenderness ratio. So during this reason, we need to make a built-up section. So there are some other reasons. Effect of bending combined with the tensile behavior require a larger lateral stiffness. So stiffness is directly proportional to the moment of inertia. More will be the moment of inertia, less will be the deflection. So unusual connection details require a particular cross section. Unusual mean that okay, if I'm having, for example, sometime if I want to connect uh, any section from the on the both side of this channel, so I cannot connect it. It's mean that if I have made a built-up section, then I connect a plate on this side and also a plate on the other side. Sometimes due to the provision of the connection, we also need to make a built-up section. This thing I will clear you when we will study the built-up member design in our next chapter, compression member design. Okay, here these are two examples of built-up section. Okay, here you can see the bridge. Okay, this bridge, I have taken this picture maybe at Dharampura bridge, railway bridge. So here you will see that this diagonal member and vertical member, they are built up. They are having one channel here, one channel on the other side, and they are connected with a small or thin flat steel bar, which are called lacing in triangular pattern. Why they have made this built up? Because load might be less, because and they need larger moment of inertia, so they are using two channels. On this example, they have used two channels whose phalanges are inverted outside, and they have connected along the length at different level with a steel plate, which are called patterns. So there are many techniques to make the built-up section. Okay, here this is the gusset plate. This is the plate. This member is connected with this plate. All the members they are connected this plate, and this plate is connected with this top cord. It means that member they are not directly connected with each other. They are connected with each other with the help of one plate, which is called gusset plate. Okay, I will not explain this here. I will first come to this slide. Okay, let's suppose we are having this steel section. Maybe this is the I section, and it is subjected to tensile force. So tensile force, if I cut this section from anywhere, here, here, or here, that tensile force is uniformly distributed along the length. Okay, at this end, we have punched the hole in this I section to connect with this column. So we have used an angle section whose one side is might be riveted or bolted with the web of this steel girder, and other side is connected with the flange of this column. Okay, since the force is acting same or constant throughout the length, so stress at an area at a point where we haven't punched the hole will be less, and the stress where at a section where we have punched the two hole, it means that area of cross section is reduced by the area that we have punched. So section AA will be this section. So in this section, on the both sides, I can say that this angle section or plates, they are welded. Okay, I can say further that if maybe I ignore these plates, no, technically, otherwise. So this is the two hole punch, so area will be less at section AA. So it means that if I am computing the area at section A, so for example, area at point B is 100 and area at point A is might be 80. So E is a tensile force which is also maybe you can compute, maybe considered constant or maybe 100. So stress is equal to tensile force divided by area at B. So stress at point B will be less as compared to the point A, because at point A there will be stress concentration because cross section area is reduced because we have punched the hole. Why we are studying this? Because the effect of these two areas will be different when it is subjected to applied load. So it may trigger two type of the failure. So failure may occur at a section where we have punched the hole, or at a section where we haven't punched the hole. So a simple example will also be given over here. We are having a truss member which is connected, which is connected with the gutter plate on the one side, and when we are connecting, so we are punching the hole along the cross section, and then we are bolting or riveting the one end with this truss. It means that if I'm cutting the section AA, at AA two hole are punched, so this is a hollow area. So area is not available. Only area, cross section area is the gray portion. At section B, we are having the entire area. So I would like to show you the picture again. So just see here at the end. So even maybe here. So how we are making the connection of this channel section with this gutter plate? We have punched the hole in the cross section. When we are punching the hole, it means that we are reducing the area. Okay, now I would like to explain from this steel uh, stress strain curve of steel. So uh, let me insert some steel shape just to make you understand. So let's suppose this will be, you can say that Fn, or maybe in the previous portion, I can say that F FA, because we have referred this section A. So let me use, this is our FA. And let me copy it again. And another limit, we might have stress acting at a section T. So again, I'm talking about in this example, stress is equal to T over A, tensile force is constant. So it means that if I'm keep on increasing the T force, so AB is more and AA is less. It means that for a same force, stress at point A will be more and stress at point B will be less. It means that I am comparing the applied stresses with material strength. So it means that the cross section where we have punched the hole, it will approach the yield first. And the cross section where we haven't punched the hole, stress will be less. Why stress will be less? Because area is less. It means that there are chances that yielding will occur first at a section where we have punched the hole. Just like, for example, here. But what happened? We know that when we are approaching to this yield point, so I would like to explain from here also. You know that at this point, so you know strain is equal to If I could insert this symbol. So strain is equal to change in length divided by total length. So strain. So when I want to compute the strain, so this strain will be equal to diameter. Why diameter? Because in this case, if I'm writing this equation over here, let's go here. So actually, this strain will be yielding strain. And if I want to determine the change in length, so this delta will be equal to this strain value multiplied by this diameter. So actually, the change in length will occur only this diameter because length of the net section just equal to diameter. So net section is the section where we have punched the hole. So the area of cross section after deducting the area of the hole that we have punched is called the net area. So the area where the reduced area is having the length equal to diameter. So again, I want to just explain that corresponding to this, just for your clarity, the yielding strain in steel, I can consider 0.005. And if the diameter of the bolt is equal to 15, then this answer will be very less. The deformation will be 0.0125. So it means that when the yielding will occur at a cross section, then the total strain at that point will be very small. So it means that the length when due to yielding occur at cross section where we have punched the hole, deformation is not very large. So the section will not fail. Why it will not fail? Because we still have a lot of reserve capacity. Because it failure will only occur when the applied stress will be more than this ultimate value Fu. So this is the case. It means that net area where we have punched the hole will always approach it to yield first. So yielding will occur only into a small length whose length is equal to diameter of the hole. So it will not cause failure because member will elongate, but elongation will be not very small. Okay, next what will happen? Next, there are two cases. Actually, why I'm explaining this? Because I want to explain the failure behavior. If we understand that what will be the failure behavior, how the stresses they are increasing in a tension member, and what type of the failure may occur. Because we want to avoid that failure. We want to avoid. First of all, we should know the concept of failure. Okay, now I'm explaining this second condition. Second condition is that when I have kept on increasing the tensile force. When I am kept on increasing, so there might be two conditions. First condition is that FB stresses at gross area, the cross-section area of the member without deducting any force, where we haven't punched the hole. It will approaching to yield. When this will keep approaches to yield, it means that we have increased load. So stress at net area will also increase, but that stress will not approach to the tensile, total ultimate stress. It means that no breaking will occur because Breaking will only occur if the stress is more than ultimate. Now, at this point, this is condition number one. Yielding has occurred at gross area. Gross area where we haven't punched the hole. So it means that in that case, if you want to compute the total strain, so total strain will be equal to change in length over total length. By total length, length of the member from the edge of this hole to the other side, because stress are uniformly distributed and gross area is available for the most of the length. Similarly, like this, gross area is available for most of the length of the member. So length of the gross area, I might consider that length is equal to maybe 100 millimeter, sorry, you can say that 3000 millimeter. 3000 means 3 meter. If the length is 3 meter, then it means that in that case, the total deflection in this member will be 15 millimeter. And this 15 millimeter is plastic deformation. Plastic deformation means that material has yielded. If I will remove the load, the member will never come back to original position. So what will happen? Steel is not broken at this point. It is just yielded. But due to the yielding, the length becomes very large. So it has been elongated to a larger amount. If I will remove the load, member will never come back to original position. So it will disturb the geometry of the structure. When the geometry of the structure will change, so the structure stability will also be disturbed. So the member will not be able to fulfill its load carrying properties. So yielding failure is actually the failure due to the excessive deformation due to the gross yielding at gross area which is available in the most of the length, but it is actually not broken. So this is the first failure condition, which is called yielding failure or yielding at gross area. So we want to avoid this failure. How we will avoid, we will discuss also. So this is the first failure. So this is provided is that Fu is Fa is less than ultimate. Okay, second condition maybe. Second condition is that we have net area is very less. Net area is very less mean that we have punched maybe many holes or maybe a larger hole. And if I'm keep on increasing the load, in that case, FA, FA means the stress at net area has approaches to ultimate limit when I kept on increasing the tensile force, but the stress at point B or section B or at gross area have not approached to yielding. So yielding is will not occur at gross area, but the stresses at net area or the area where we have punched the hole has exceeded the ultimate. When the stress will be more than or equal to ultimate, the member will break. It will split up. It will tear apart into two parts. This means that this will be referred as a rupture failure. Rupture at net area. Net area, the area where we have punched the hole. So now I will come back and I will explain it again. So we are technically having two types of the failure. One will be the failing may either occur due to the yielding at the gross area or rupture at the net area. So we want to avoid ultimate stress to approach at net area, but at the same time, we do not want the stress should exceed the yield limit at gross area. And how we can do, now we will discuss it. So based upon this, we are having two equations. So in this two equation, but let me add a slide and let me explain. So in this case, For a time being, forget about this equation. We are having a general equation which is referred as load effect. Effect should be less than equal to capacity. So this is our basic equation. And we, to bring this equation to the safe limit, we multiply with factor of safety. And if we want to write this equation into a general equation, so we can, this is A, RA, and then it is multiplied with factor of safety. So RA means that this is the applied load effect. This is just general equation. Why I'm writing it over and over again so that you may memorize. So this was our basic equation, and we refer resistance of a material by a parameter which is referred as Rn. So next I told you that we are using this equation as if multiply with phi. Why we multiply this by phi? Because in LRFD, we multiply the applied load effect with factor of safety, but at the same time, we are reducing the capacity by multiplying with strength reduction factor, which is 1 over F2. So Rn may be capacity in any behavior, maybe in tension, compression, and Ra will be any load effect. So now this is our general equation. So in this general equation, our applied load in case of the tension member may be equal to Ta, and our Rn might be the tensile capacity, Tn. So we are comparing that applied load effect should be less than tensile capacity. And I can further write this equation into another way. So how I can write? I can write that Ta multiplied by factor of safety will be equal to Tu. This is the applied factor load. Applied tensile factor load, if service load they are multiplied with the factor of safety, so they are referred as factors. So this is our basic design equation. So how to compute this capacity? So I'm just writing this formula over here, or simply, so now in the next, we how to compute the capacity. We know that stress is equal to load or force over area. So if applied stress F, we represent the stress by F, or you can say that small f, okay, no problem. Let me use the symbol F. And that might be equal to, so I'm considering the applied load may be equal to tensile load. So I want to compute, and that area will be equal to A. So from this equation, I can say that applied load may be tensile. T will be equal to F into A. So this T, I can say that if I know the stress, this is equal to capacity. This will be equal to capacity of a member, Tn. and Tn capacity will be equal to F material strength multiplied by the area. If I'm multiplying the strength of material, if a section is already built with the area, then I will have its tensile capacity. So from this equation, if I multiply, I will substitute this value over here. Tn will be equal to Fy. So here, now I'm replacing this Tn with F dot A. So technically, this will be my equation number 1. Okay, now if I want to consider a yielding failure, if I want to consider yielding failure, okay, just let me write now this equation separately. So in case of the yielding failure, so I have told you that in case of yielding failure, failure means that yielding failure will occur when applied stress will be equal to or more than yielding. So I have to use the strength of steel as Fy. Yielding failure means that which is occurring due to yielding. And yielding will always occur at gross area. Gross area means that which is available for most of the land. So this will be my first equation. So first equation is that yielding capacity at gross area should be more than equal to applied load. So how come I have derived this equation? TU is the factored load or applied load fact should be less than equal to material capacity or capacity of material which is having a certain cross section. So here I have considered the capacity yielding at gross area. So here I can modify this equation again also. So this equation will be like this. So in this equation, I'm considering the rupture failure. Rupture failure will always occur due to ultimate stress when applied stress will be more than equal to ultimate stress. And this stress will always occur at a net area. So this is my two capacity. Later on, I will change with net area with another area, but I will explain when I'm discussing that topic. So here it means that I'm having derived two equations by using basic design equation. What is basic design equation? Applied load effect should be less than equal to material strength. So here, again, now you will be able to understand this. So phi t Tn capacity I have just written that is the capacity in yielding, and phi t Tn is equal to phi t Fu, and that is the capacity in fracture. So both these capacity should be more than equal to applied load effect. So I'm having two equations. So here the this strength reduction factor will be different in yielding, and that will be different in case of rupture case. Yielding case, code says that use this value as a 0.9, and in case of rupture, use this value as a 0.75, lesser value, due to the sensitivity of the failure. Because yielding failure will not cause progressive failure or complete collapse of the structure. So that's why we have reduced the material strength just by 10%. But actually, rupture failure is a serious failure. If this failure will occur, that may cause progressive failure or collapse of the complete structure. So here, what we must say that we have to use a larger phi t value, and these values are recommended by code. So design strength is either be computed due to the rupture at net area or due to the yielding at gross area. Now here I will explain that what are the gross area. So it is the total area of cross section present throughout the length of the member. Total area which is present throughout without punching any hole. The elements which are discontinued lengthwise are not included. For example, area of lacing element and spacer plate is not included in the cross area. So here, how I can say that just like here. So you will see that along the length, lacing is also available. at any cross section. For example, at this cross section where the bed ends, so I need to consider also the area of the plate also, because area is more, but I will not consider, I will ignore it, because this plate is not available throughout the length. At this section, only two channel sections are available. So that's why we are showing the lacing and other connecting element which are connecting two sections to make a bit of section. We are ignoring it. So this is the gross area. The gross area for rolled steel shapes is directly available in properties table. Properties table, I have already shown maybe in the previous lecture the properties table. Maybe I will show you again. So you don't need to compute the area. This area is directly provided by AISC Steel Construction Manual, or you can refer the book by Dr. Zahid Ahmed Siddiqui, LRT Design Aid, and you can uh, see or check the area of any section which is given from the starting page. And here you will see that, so for any particular section, for example, for W530 and 150, the gross area can directly be obtained from steel sectional properties table. So you don't need to compute. That's why we are referring this. Why the area is directly available? Because this is a standard section. Standard section means that the people, the vendor or the factories, they have manufactured this section as per the requirement given by AISC. So AISC said that if you want to make W530 into 160 section, 50 section, this area must be 19,200, and that will be only possible if it is having the depth 544 millimeter, width of the plan 312, thickness 20.3, thickness of the web 12.7. So if we are having this value, this geometric dimension, then area will be this. And we also know all the geometric properties. And the next is net area. So net area is the area that we obtain after deducting the area of the hole that we have punched. So why we are considering net area? Because if we want to compute the capacity at in rupture, so rupture will always occur where we have punched the hole. So rupture strength is the function of the net area. So net area can be computed by deducting the area of the hole that we have punched to accommodate the rivet and the bolt. And failure of tension member always occur at the weakest section where the area of cross section is minimum. So throughout the length, we have to check where the net area is minimum, because rupture will always occur at a point where we have punched larger hole. Cross section, not along the length area, because tension member, when we are applying the tensile load, so breaking area is perpendicular to the length. So according to AISC D32, the specification given in the chapter and D and class 3.2, the net area of member is the sum of the product of the thickness and the net weight of each element. So I will explain how to compute. So net area is the net width multiplied by thickness. Okay, sometime this is the last point that I will explain before the break. Okay, just from the previous point that I have explained, this is the net area. Actually, sometime what we do, now I am more interested. We actually are not using the net area, rather we use the effective area. And what will be the effective area, I will explain now, and why we need to compute this effective area. So effective area is equal to, we are having one factor which is referred as shear lag factor multiplied by net area. Or in other words, we can say that we are having a value u which is the equal to ratio between active area and net area. So this, so actually this capacity is, we don't use the net area, rather we use an effective area. And why we use this area, I will explain. So U is the shear lag factor, which is always less than 1. So what we do is mean that we multiply net area with a value U whose value is less than 1. So effective area is always then less than net area. We are further reducing net area due to certain reasons. So shear lag factor is the factor which is less than 1 and which is used to convert the net area to the effective area. So why we are considering this factor? So bearing pressure due to the, actually there are two reasons, you can read it, due to the stress concentration and eccentricity at the joint. So what does it mean? When we are connecting two members, for example, this is the angle section and this is the gutter plate. When this gutter plate is connected with this angle section, let me check, do I have an example here? Okay, here. So here you will understand that the center line of this angle section is over here, centered, and the center line of this gutter plate will be somewhere here. So it means that distance between the centroid of the plate and center of the angle section, they are having certain eccentricity. So it means that at the connection, due to the eccentricity, some extra moment will come. So from here, when the load is transferred because the angle section is not, the center line of the angle section is not coinciding with the center line of the other connecting member. So when the at the load transfer point, which is transferred at the bolt, there is a eccentricity, and due to the eccentricity, there will be some extra stress will come. So when the stress will be extra, it means that if you are estimating the stress as 100, but due to the eccentricity, there will be some movement, and movement is causing some extra stresses, 20 megapascal. So it means that stress will be more. So what is the definition of the stress? For example, from here, I can write over here. So there are two ways. Actually, there are two possibilities. Stress will be plus, there will be some extra stress due to bending moment, and due to bending moment, stress will be equal to m y over I. So it means that actually it is difficult to compute this extra stresses. This moment will be equal to T into E. So we cannot compute these stresses. So this moment will be equal to T dot E. Dot E means that that's due to the eccentricity between the center line of angle section and channel section. So actually that will be the actual stresses. but actually it is difficult to compute these stresses. If the total answer will be this is 100 and this answer might be 25, the total stress will be equal to 100. So what we do, this value is equal to AN, net area, because I'm computing the net stresses, this sorry, the stresses at the net area. So what we will do, we are ignore this value, and I can reduce this net area by multiplying this U factor, which is shear lag factor. This means that if I reduce the area, so less will be the denominator, more will be stress. So I am considering these bending stresses indirectly by reducing the net area. So I am assuming that due to the applied moment, extra moment which is produced due to the eccentricity between the two connecting members, section with the gutter plate, the area is reduced. So this can be considered as a T over An. So due to two reasons. Number one reason is due to the eccentricity. So this area will be referred as the effective area. Which means that if I'm reducing the area, so stress are increased. So I'm increasing the applied stresses due to this moment case. So this is one due to the eccentricity. And other will be the stress concentration. Stress concentration means, what is stress concentration? Actually, here you will see that first, this is the angles edge I section. When we are using the I section, so we need to use two gutter plate on the both sides to connect it with the other member. So in this I section, the force is completely distributed in the entire cross section. But at the connection part, half of the force is transferred to the one gutter plate and half to the other. Or in this case, you can say that force is transferred to this gutter plate with the help of this bolt. So at one cross section, there is only one bolt. It means that at this section, force is resisted by the entire cross section, but at this section, force is transferred to the cross section area of the one bolt. So area of the bolt is very less. This means that at this point, there might be stress concentration. Stress concentration means that due to the reduced area, stress will be more. So how we can consider this area, this extra stresses? So we are converting the net area into the effective area by multiplying with the shear lag factor. So shear lag factor is a ratio between effective area over net area, and its value is always less than 1. And why we consider? Due to two reasons: stress concentration and due to the eccentricity. Similarly, at a connection, if one part of the section is connected while the other is left free, all forces have to pass only through a connection part of the member. Just like in this case, all force is transferred with the help of this vertical leg to this part. So these are the reasons, and here there are some sample cases. So in this case, how we can prevent these cases? So we can compute the shear lag factor due to the efficiency of the joint. Efficiency of the joint mean that we must compute or provided sufficient bolt along the length so that the force is completely transferred from the one part to the other part. The efficiency of joint is defined how well the stresses are distributed or transferred from the one part to the other part. If joint is not fully efficient mean that if we are not transferring the force properly from the one part to the other part, if there might be stress concentration, it may cause premature failure. Premature failure means that you have estimated the tensile capacity 100 kilonewton, but actually the member failed at 80. Why it failed at 80? Because you have ignored some extra stresses which are being produced due to the eccentricity or stress concentration. So due to this reason, we are converting this effective area into the net area. So at a moment, maybe I would like to have some break, maybe break of let's suppose 12 minutes at my, okay, 15. At my watch time is 11:08. So I will resume the lecture at 11:10. Oh, sorry, 11:20 or 22 between. Okay, anybody, if somebody is having the question at the moment, he is most welcome before the break. Any quick question?
Sir, actually,
Okay, please
may
do not ask direct question. Use the raise
sorry,
your hand
sir.
option.
Sorry, sir.
Yes, yes, Sudhashri. Yes, what is the question now?
सर एक्चुअली में जब हमारा जो लोड एंड पे जॉइंट कनेक्शन पे जाके ट्रांसफर हो रहा है वो तो सिर्फ बोल्ट से ट्रांसफर हो रहा है तो उधर फिर हमारा बोल्ट का ही एरिया जो है वही मैटर करेगा फिर।
Okay, very good question. Okay, we will also design the bolt. We will also design the bolt for that case. But let me know how much area of the plate is in contact with the bolt. Only small portion of the plate is in contact with the bolt. You understand? So it means
यस
that
सर।
so this small plate, it means that not entire length of the plate is in contact with the bolt. It means that I am considering the stress concentration in plate, which is in contact with the bolt, which is a circumferential area or the circumferential portion of the plate which is in contact. When we will consider the bolt, so we will consider the bolt stress in our design case. So it means that a small portion of the plate at the section at connection is transferring the load as compared with the section where we haven't considered load. You got the idea now?
यस सर, ओके
Okay.
सर, थैंक यू।
Okay. Okay, maybe at the end of the lecture, I will also take the questions. So during the lecture, if you will have any question, please write it on a page. And also during the lecture, you must have LRFT design aid with you because I will ask you, okay, please open up this page and see the table is given or not. So this is always a good idea. Otherwise, it will be difficult for you to understand the entire concept. So inshallah, I will see you after 15 minutes of the break. See ya.
यस सर।
Okay, let me start the recording. Okay, Bismillahirrahmanirrahim. Okay, before the break, we were discussing the shear lag factor, and I was explaining that how to compute that shear lag factor. So, shear lag factor is used in order to reduce the net area due to two reasons. We may have either the stress concentration or eccentricity at the joint. This means that shear lag factor will only be used with the net area in order to compute the rupture strength or capacity in rupture. So shear lag factor you can say that a ratio between effective area over net area. So what are the different value of shear lag factor? So how we can see? So these shear lag factor values are specified by AISC. So uh, shear lag factor actually when tension load is transmitted through the each of cross section element by fastener or weld, when entire area of the one cross section is in contact with the entire cross section area to be connected, then shear lag factor value will be equal to 1. But in all other cases, we have to compute shear lag factor by this equation. So this shear lag factor is the function of also referred as efficiency of plant. So this shear lag factor is equal to U is equal to 1 minus x bar over L. So we can compute shear lag factor by this simple equation. So it means that this factor is being subtracted from the 1. It means that this value will always be less than 1. So what is x bar and what is the length? Here L is the length of the connection, total length of the connection. Not it is with reference to the length. I will show you the next diagram. And x bar is the uh, eccentricity of the member which is being connected with the other element or other structural component. So we will see what is this x and what is this L. So x is the distance from centroid of element being connected eccentrically to the plane of loading transfer called connection eccentricity. And the L is the length of connection, center to center length of outer rivet hole or actual length of weld. So here in this next slide, so X is, for example, we are having this angle section which is connected with this gusset plate. So X is the distance from the centroid of the angle section to the outer face of the gusset plate. So maybe I have shown you this diagram over here. So this was this diagram. So in this diagram, so here, so it is, for example, we are taking distance from this outer face of the gusset plate to the centroid of this angle section. That will be referred as a x bar. And in case of a Z section, is in contact with two gusset plates on the both sides. It means that half of the T section is behaving as a one unit on the one side and half is behaving on the other side. So just excuse me. Last one. Okay, sorry student, due to the some interruption. Sorry. Okay, in case of our I section, actually half of the I section is connected with the gusset plate from the one side and half is connected on the other side. This means that if one half side is connected with the one side, so half section it is just behave like a T section. So in that case, for the half section which is as a T section, we have to determine what is this centroid of that equivalent T section and the distance of that centroid. Distance of the centroid of the corresponding T section to the outer face of the plate. Actually, you also don't need to compute this x value in case of the centroid corresponding to T section. And this also x bar value, this value is also not need to compute. These are also directly given in LRFD design aid. So here I will show you again LRFD specification. So how you can get this uh, value. So here, for example, in LRFD specification, if you are consulting the section property table for W section, so at the top left corner you are having this layout. In this layout, this K is the distance from the top face to the centroid of T section. So in this case, only T section is considered. So this value is referred as a K. So the K is the distance from the top face to the centroid of half section or T section. So it means that you can directly see this value from the LRFD design aid. And this K value is mentioned over here, for example, for W530 into 300, so K value is 54.1. It means that in this equation for this I section, you will substitute the value, X bar value equal to K. And for this angle section, this is the centroidal location that can easily be obtained from LRFD design aid test sectional properties of the angle section. And then what is the L? L is the total length of the connection. So total length of the connection means that length along the length. So if we have welded both sides of the section and the length of the larger weld will be equal to length of connection. And along the length, if we have connected with the rivet or the fastener, then center to center distance between exterior center to center, not here I have shown maybe from the edge, but this will not be from the edge. This will be from center to center, distance from the two exterior board. This will be the length of the connection. So if we are increasing from, for example, in this formula, shear lag factor can be increased or efficiency of the joint can be increased, either increasing the length of the connection. So this is properly used in the connection phase. So for all the other part, so effective area will be equal to net area multiplied by shear lag factor. So when two separate plates are connected, so if the length of the weld is more than equal to 2 times of the width, for example here, this length width of this cross section is B. Let's suppose if the length of this connection is more than 2 times of this B, then shear lag factor will be equal to 1. And if it is between, it is less than 2B but more than 1.5B, we can assume by Dr. Zahid Siddiqui. So you don't need to memorize this value. So a table is provided. So depending upon the condition given, you can consult the value from this table. So for WMS and HP, WMS, HP all are the I section, double symmetric I section or Ts with flange connected with 3 or more than 3 fasteners. 3 or more than 3 fasteners in one line. We can provide the bolt either in 2 lines or in 1 line. So here I can say that just to highlight this. So 3 or more or height of the girder 2 by 3 means 0.67, then shear lag factor will be 0.9. And if BF value is less than 2 by 3 of the depth, then use this value as a 0.85. This value you can use if we already know the sectional properties of this I section. So this is the given in point number D and point number E. If you have opened page number N98 on LRFD design aid. Similarly, for WMS and HP section. HP section means that where these are the I section or T with web is connected. Okay, here point E is for if flange is connected, flange. But if I section is connected with web, web of I section is connected with gusset plate, and if the fasteners are more than 4 or 4 equal to more than 4, in that case shear lag factor value we will use as a 4. And for a single angle section with 4 or more fasteners, this is for single angle. If in a single angle we have used 4 or more fasteners per line, then we have to use the shear lag factor value 0.8. And for a single angle section with 2 or 3 fasteners per line, then shear lag factor will be used as a 0.6. For example, in this particular case, along the length of the member, we have used 2 fasteners. So angle section is connected with the gusset plate with 2 fasteners. So in that case, shear lag factor I will use as a 0.6 because that is specified by AISC. And for all the other case for the plate where the values are not given, we can compute by this formula. So you can consult the page number 98 and 99 on LRFD design aid. So next is the calculation of a net area. How we can compute a net area? Yes. So I will explain these slides, but first let me come to this part. So actually, uh, maybe you will be able to understand from here, but I will try to explain it. So in this case, so let's suppose this white area is the area of the hole that I need to punch. Punch means that, for example, I want to use a rivet. Maybe that might be bold or that might be rivet. Okay, let me write as a rivet. Okay, if I have want to connect one plate with another plate with a rivet whose diameter is equal to 15 millimeter. So what do you think? What should be the size of the hole that I will punch? Then the area of the hole that I have punched should be more than the area of the rivet so that I can easily accommodate. So it means that I have to give the margin on both sides as 0.75 plus 0.75, which is the margin given on the both sides. So it means that I need to provide some extra margin on the both sides as a 0.75 and 75. It means that diameter of the total hole should be 1.5 millimeter more than the area of the rivet or diameter of the rivet. So this 1.5 is the extra margin that I am punching or extra diameter that I need to punch to accommodate the hole easily. But further, when we are punching the hole, so during the punching process, you know that the edges of the hole they damages. So when the edges they are damages, so we consider that the area of hole has increased. So we further increase a total diameter to 1.5 to accommodate the wear and tear at the edges. This means that when we are punching the hole, the total area of the hole that we need to punch will be equal to diameter of the rivet plus 3. So it means that in fabrication, structure steel which is to be connected with the rivet or bolt, the hole are usually punched larger than diameter. Furthermore, the punching of hole is assumed to be damage or even destroy 0.75 millimeter or more of the surrounding metal. 0.75 on both sides. So total will be 1.5. So in that case, our diameter of the hole will be that we are punching will be equal to diameter of the rivet plus 3. So in this way we can compute. So diameter of the hole for rivet is D plus 1.5 where another 1.5 millimeter is to be added because the extra portion around the hole may be damaged due to the drilling of the hole. So in that case, what I can say that what is the total reduction? So this is the total width that we are reducing. And actually, we this on the other side we are having thickness of the section, so we need to multiply this diameter with this thickness. So for example, this is the cross section at the net area, so it means that we have to subtract this whole side. So what area we are subtracting? Diameter of the rivet plus 3 multiplied by thickness. It means that we have to subtract this area in order to compute the net area. So what is the formula? Reduction of the area in case of the fastener. So we may have two type of the fastener, maybe rivet or maybe bolt. So reduction of the area will be equal to diameter of the rivet plus 3 multiplied by thickness of the plate. So again, I would like to explain, I will explain when we are computing this. So in this case, if I want to compute at any cross section, at this cross section only one hole is here. At this cross section only one hole. So at this cross section, so diameter of the hole plus 3 multiplied by thickness of this angle section will be the area that I need to deduct from the entire area to compute the net area. Okay, but this formula is different for the bolt. For the bolt, we are having the formula diameter of the hole for bolt plus 2. It is not 3. And what is the DH value? For example, if we are provided the diameter of the rivet 15, so that value will be 15 plus 3. But if we are using the diameter of the bolt as a 15, then for the 15 diameter of the bolt, hole size will be different. And this hole size can be directly seen by a table which is provided by AISC. So let me check where this table is given. On LRFD design aid, uh, this table, I'm just checking. So, sorry, this table. So if I want to use the diameter of the bolt as a 15, then DH value will be 17. So you don't need to memorize this value. These are provided there. So let me, they might be at the end. Because the main thing is that you need to consult the LRFD manual in your examination. So you must know that where all these values are given. Yes, I have got. So page number 310, not 310. Yes, page number 309. So this table is given on LRFD design 8, page number 309. So on the page number 309, so if in this statement it is said that compute the reduction in the net area or the net area if we are using the bolt size 20. So for a bolt size 20, diameter of the hole will be 22, and further you need to subtract, maybe add 2 value. So why we are adding 2? This 2 is the to accommodation the damages. So D is the diameter of the rivet and DH is the diameter of the a hole for a standard bolt. So reduction in area for more than one hole. So reduction in area will be n d plus 3 into t. So this is the reduction of the area for one hole at cross section, not along the length, multiplied by n. If there are more hole at one area, at one cross section, so we need to multiply it by 2. So net area will be equal to total gross area minus reduction of the area due to the hole that we have punched. So I will give you the example. So example is given on this page. Okay, on this page, on this slide is example number 2.1 in LRFD manual. So what is the problem? Determine the net area of 110 into 200 plate joined with 6 into 200 plate as shown. So it means that, okay, just see we are having a larger plate. So this plate is having thickness 10 millimeter and width 200. And these two smaller plates are each 6 millimeter and width is again 200 millimeter. Okay, see here. 4 bolts are provided along length in 2 rows. So we have provided 4 bolts in one line and 2 lines are provided, but at any cross section, because tension member will always break perpendicular to the length. So at any cross section, if I consider, for example, this cross section, okay, if you may either consider this cross section, this one, or this one. So at any cross section, there are only 2 holes they are passing. It means that at any cross section we have to consider two holes. Okay, now because if the total force T is acting in the large plate, so on the smaller plate, the force will be half. So there are two possibilities. Either the larger plate will break or two smaller plates will break at the same time. And first we need to compute the gross area. And gross area will be used whichever will be the lesser out of the larger plate and two smaller plates. Cross section area of this plate will be 100, 200 into 110, which will be 2000. And gross area, cross sectional area without punching the hole of this two small plate will be 6 multiplied by 2 and further multiplied by 2 because we are having two plate, that will be 2400. If we are punching the hole again in the larger plate and smaller plate, gross area of two smaller plate is less. So it means that, sorry, gross area of larger plate, thicker plate is less as compared with the combined gross area of two smaller plates, which is 2400. It means that rupture may occur only in the larger plate. Why larger plate? Because if we are considering the one single plate, then force is half. So I'm considering two combined smaller plates and thicker plate as a sole plate. So gross area will be smaller out of the thicker plate area and area of two smaller plates. So which is 2000 is the gross area, cross section area for the thicker plate. Okay, now net area will be equal to gross area minus n into d plus 3. Okay, we have to see that what he has given. So we have to use 20 mm rivet. 20 mm rivet means formula will be used n d plus 3 into d. So D is the diameter of rivet 20. 3 is the extra margin, which is the margin of the hole to accommodate plus damages considered. And 2, why 2? Because at any cross section, there are two hole punch cross section because failure will occur perpendicular to the length. So N value is equal to 2. So net area is 1544. So in this case, our net area will be this one. Okay, here uh, we shear lag factor will be equal to 1. Why it will be 1? Because eccentricity on the both sides. One tensile force will tend to produce the moment on the one side, and this T by 2 tends to produce the moment on the other side. But anyhow, we may compute if you want. How you can compute? You can take the center to center distance from this thicker plate to the other plate, and length of the connection will be the distance from the center of this two exterior board along the length. So this will be the computation of the net area. So I will stop my lecture here. So I will start in next lecture from the computation of the if we are having bolts not in one line, then how to compute the net area. So in the meantime, if someone is having the question, he can use the raising hand option and can ask me the question. Any no other questions are welcome. Yes, Udashiti, please ask the question.
सर हमारे पास रिवर्ट के लिए 3 mm मतलब इंक्रीज है और बोल्ट के लिए 2 है,
Yes,
तो ये
yes.
डिफरेंस
No.
क्यों?
You did not understand. I told you that for the rivet, the increase is 3, but this 3 is into two parts. 1.5 is the extra margin to accommodate the hole, and 1.5 is the damages that we are considering due to accommodation of the hole. Actually, in case of the rivet bolt extra margin is not 1.3. Extra margin is the base depending upon the bolt size. It means that if I could have used in this example the diameter of the bolt as a 20, in that case I need to punch the hole of 22 millimeter. So extra margin is 2 millimeter to accommodate the bolt of 20 millimeter. So DH value I have to use. So plus 1.3 because 1.3 I need to consider the damages due to punching of the hole. But we are rounding that 1.5 value and we are using 2 value instead of 1.5. So that answer is this one. So here what I can say. So DH value it including this is not the diameter of the bolt. That is the standard diameter of the hole, which is larger than the bolt diameter, which is taken from the AIS specification. So it means that 1.5 or 2 is already included here, the extra margin. And this is the margin to consider the damages due to punching of the hole. So this value is supposed to be 1.5, but we have rounded it to the 2. So DH plus 2, DH is not directly the diameter of bolt. That is the diameter of the hole for a standard bolt. And DH value we can taken from a table given by AISC and also given on LRFD design aid as I have explained. I think that I have made it clear. You understand? That?
Yes. Okay, sir.
Okay. Anybody is having quick last question? If you will have any further question, you can send me your queries in the chat box also. So please let me know if you are having any questions. Okay, gentlemen, if you are not having any questions, so I would like to conclude the lecture. Inshallah, see you the next time. Allah Hafiz.